Hey there, class. We're here today to look at example 10 if you're in my physics 1 or example 8 if you're in my honors physics class. And these are from your notes in work and energy. So we have here a ball is being dropped from a height of 25 meters, and we want to find its speed at impact. So what we're doing here, again, remember this is the speed at the impact, not after it's come to rest on the ground. We are told that we are supposed to ignore air resistance. So when I see this, what I'm thinking is conservation laws. All right, so I'm thinking conservation of energy because the force of friction, in this case, it's the drag force due to air resistance, is a non-conservative force. So non-conservative force that we have. And so since we're ignoring it, basically that applies to the conservation of energy. So certainly we have done problems like this in the past. You probably remember in vertical kinematics that we can certainly do this. We know that there's an acceleration because of gravity, and that acceleration due to gravity, of course, is 9.8 meters per second squared. So we could certainly approach this from a vertical kinematics standpoint. However, we're going to look at this more from the energy standpoint and kind of approach this from a different way of looking at this. So here we go. Here's how we do this. So let's take a look at where the ball starts. The ball starts here at the top, and because the ball is starting at the top and it's also starting from rest, in other words, the velocity equals 0, the ball was dropped, that means the kinetic energy, which is 1/2 mv squared, because the velocity is 0, that is going to actually have 0 kinetic energy. Now, the ball is also some height above the ground, so it will have kinetic energy. It has mass, there's gravity, and there's a height. So this ball will, in fact, have a calculatable, it's going to have a calculatable amount of potential energy. So that height was 25 meters. And so the total energy we start with, if we sum these two things up, because there's no kinetic energy, we can ignore that. There is simply potential energy at the beginning. All right, let's look at what happens as it falls. As it falls, the height is, of course, decreasing until a point where it reaches the ground. And when it reaches the ground, there is no potential energy because here at the end, the final height is actually 0. And so at the end of this problem, at the end of this situation, there's going to be 0 joules of potential energy. Now, kinetic energy, on the other hand, again, is 1/2 mv squared, and the velocity at this point, because it's moving here at the ground, again, remember, this is at the instant it hits the ground, this is its final velocity, is a non-zero number. So there will, in fact, be kinetic energy. And so the total energy in this problem, at the end, the final energy, is going to be just the kinetic energy, 1/2 mvf squared. Now, let's go ahead and take a look at a strategy on how we might go ahead and solve this. Okay, so our goal in the end is to find, in fact, I think it just says speed, so we're really looking for the magnitude of this. So this is the goal of our problem. The mass is actually an unknown quantity at this point in time. Now, that's going to bother you, some of you, because you're going to say, well, I can't calculate anything without mass. I promise you, if you stick around and watch this through to its duration, you'll see why that isn't a concern at this point in time. Initially, the velocity at the beginning is 0, and it starts at a height of 25 meters. We know that gravity is 9.8 newtons per kilogram here on Earth. So, and then lastly, the final height is 0 meters. So let's go down, let's put this into a strategy and implement our strategy. So, because we are dealing with conservation of energy, And again, the reason this is conservative is because the only force that really acts on this object is the force of gravity. That is a conservative force, so therefore we can use the conservation law. If there was air resistance, we'd have to incorporate that in, and it would do work to this system. But that's not happening here, so we'll save that for another example later on. So to implement our problem here, basically what the conservation of energy says is that the total energy at the beginning has to equal the total energy at the end. Now our total energy at the beginning could be due to kinetic energy plus potential energy. Now, as we discussed earlier on when we talked about what we understood, we already knew that this was going to be 0. Likewise, on the right-hand side, our energy could be due to potential energy at the end plus kinetic energy at the end. And again, we've already discussed this, but because the ground is where this ends up, it's going to have 0 potential energy. So basically what this ends up as is the potential energy at the beginning has to equal the kinetic energy at the end. And this is where I can substitute in my, I'm going to substitute in the expressions for these. So the expression for mgh will calculate us the potential energy. And over on the right-hand side, we're going to have 1/2 mv squared. So that's not a squared. That's a squared. And that's at its final velocity. Now, ultimately, you're trying to solve for this. Okay, that was our goal in the whole problem, was to solve for the VF. So this is the part where some of us were concerned a little bit about the mass, and we didn't know it. We said, well, I don't think I can find this. But I'm going to show you right now that that actually doesn't matter. So to get the VF by itself, I'm going to divide by 1/2 m, and that will, on this side, cancel out the 1/2 and the m. Over on this side, we're going to divide by the 1/2 m. And you'll notice here there's an m on top and an m on the bottom. They cancel out as well. What this will give us, if we do if we divide by a fraction, you'll actually end up with multiplying by the reciprocal. So basically we end up with 2gh original equals VF squared. I still don't have the VF by itself, so I'm going to need a square root. That's going to undo the squaring. And what I'm going to end up with here on the left-hand side is the square root of 2 times g times original height equals the final velocity. In this case, just the magnitude. The direction isn't all that important. So let's go ahead and substitute in some values now. We have 2 times 9.8 newtons per kilogram times the height, which was 25 meters, and I'm going to square root all that, and that's going to equal the final velocity. I'm going to get my calculator out here and figure out what that equals. Putting this into my calculator, I end up with 22.14 seconds. So the response to our question, which was how fast is it traveling at impact, then it of course will be traveling at 22.14 meters per second. Now in a previous video, we had talked about this, and we had a slightly different situation, and I'd like you maybe to refresh your memory with that video on another example problem. And what we're going to do is we're going to discuss how this situation and that situation, as far as from an energy standpoint, are actually 100% identical. So that's a topic for another video.